Hi everyone. This video gives you a summary of the design and analysis techniques related to the feedback circuits. So the first question is really, what is the purpose of analysis? Because any circuit, including a circuit with one or multiple feedback loops, can be always analyzed using the classical circuit techniques such as nodal analysis or using the circuit simulator. So one may ask the question, so what is the point of having specific techniques for feedback analysis? Now, and that's a valid question, and it's only useful, these techniques are only useful to the extent that they provide additional insight or design guidance as far as the gain and stability, bandwidth, sensitivity, and linearization are concerned. So they're only useful to the extent that they can help you with the design or can provide additional insight. So for this purpose, in this video, we'll only focus on the methods that are useful for design and insight. And specifically, we'll talk about asymptotic analysis based on return ratio. So we'll talk about asymptotic transfer function calculations first, which is basically the most important and useful part of feedback. And then we'll talk about what are the two correction factors associated with that. We'll talk about a Blackman gain formula, which is a very useful tool for not only determining the input and output or port impedances in general of circuits, but also they are very useful in terms of design. So if you want to design an amplifier that has a high output impedance or low output impedance, how would you use feedback to achieve that design, which is a more important and useful question. And then we will talk about loop gain, which is a valuable tool in assessment of stability of feedback system. And we'll talk about that in terms of calculation and determination of loop gain. We'll talk about unilateral and bilateral loop gain. So with that, let's get started with our conversation. So the generalized circuit amplifier is shown in this figure. And keep in mind, this is not an op-amp. This is it could be an op-amp is an example of this thing, but it's much more general. So basically, this amplifier has two inputs, UI plus and UI minus, which can be voltages or currents. They are of the same type. So they're both either currents or both voltages, but they can be voltages and currents, and a UO, which is an output, which also can be a voltage or a current. So you can see that it's more general than a typical voltage amplifier or an op-amp. And the basic property of this box that we'll use quite frequently is that its output is some gain times the difference of the two inputs. Now, of course, if the output, for example, is a voltage and the two inputs are currents, then this gain will have units of ohms. So we'll have units of impedance or resistance, and all sorts of variants on this exist. So then the question really is, how do we use this and how do we apply feedback to this? Now, for now, we assume that this amplifier is unilateral, meaning that the signal only flows from the left to right, basically from its input to its output. So now let's start with a basic feedback configuration, which basically means that if we apply some network, so we are talking about circuits here, really, both A and F consist of circuit elements, that takes the output, is it a voltage or a current, and feeds a fraction of it with some behavior back to one of the inputs, the UI minus. Now, of course, now the input, the difference of the two inputs is UI plus minus UI minus, which gets amplified by A. And now UI minus is given by F times Y, as you can see in this equation. So if you plug F times Y as UI minus, and input being X, UI plus is X. So what you have, and then you can easily solve for the ratio of Y over X, and you get the classical formula that you're probably familiar with, which is basically A over 1 plus AF in the context of circuit. But now remember, this A can have units of ohms or Siemens or what have you, depending, or it could be unitless if it's the voltage, and depending on what you have as input and output. Now, this basically is now also, this also assumes that the feedback network is also unilateral. So both of them are unilateral. So you have a unilateral loop essentially. Now this is the interesting part. So we are getting to what we call the asymptotic transfer characteristic, which really is what captures the essence of the useful part of feedback, how you want to use it. So, and the way to do this, and we'll see this in many examples, the idea here is that you don't scale the parameter of the transistor or the amplifier. In this case, you don't make A larger. You add a new scaling parameter, K, and you scale that up. And this is important because, in some nuance, especially in the transistor level circuits, this will have an impact on the way your calculation work out. So now let's say you introduce a factor K, which is shown here in this equation. Of course, if you make your gain from A to Ka, the first equation that you had becomes Ka over 1 plus Kaf. Now the asymptotic part comes in play. Basically, the asymptotic part is that interestingly, when you take k to infinity, this expression reduces to, in this example, to 1 over f. But in general, this is what we define as asymptotic transfer characteristic, and we show it as h sub infinity. So this is basically what the transfer characteristic, whether it's a gain or transimpedance or what have you, it would be ideally if you had infinite amount of feedback applied. And you will see that basically by taking k to infinity, you get that it's basically the feedback can be defined, f, the value of f, especially in a circuit where you can't sometimes tell where the forward circuit begins and ends, when the feedback network begins and ends. You can actually use this to define f or find f, the feedback factor, as 1 over h infinity. Regardless, the important value is the h sub infinity or asymptotic transfer characteristic. Now, the interesting things about this is that what you see in this example is that when k goes to infinity, this becomes independent of a. So meaning that if you make this large enough, you can make the amplifier, the feedback network, independent of the forward gain. And this is one of the key features of what makes feedback circuit useful, especially if you have a large amplifier. So a lot of times you make an amplifier with sufficient amount of gain that you don't care about its exact value of gain or its variations. And we'll see, talk about that a little bit later as well. And that in that case, you can define the forward closed loop gain or h infinity to be ideally as 1 over f. And there would be some correction factors that shows that kind of like under the right circumstances, it would not be exactly 1 over f, it would be a little bit different, but you can calculate. And and again, I would like to emphasize this, that h infinity represents what the ideal feedback, what the feedback circuit should ideally look like. What would it really look? Now, this brings us to an important principle. It's very useful for analyzing, especially in analyzing transistor level circuits and also op-amp level circuits, which is what we call asymptotic equality principle. So the idea here is that if you have negative feedback, and this is an important thing to verify first. So any circuit you want to apply to this thing, you have to have at least a low frequency negative feedback. And you see in this case, for example, in this example, you do have negative feedback. If you, for example, the output goes up, then the output of the feedback network goes up, which basically takes the UI minus up. And because of that minus sign, the output is going to be pulled down. So you have a negative feedback. And now if you have it, such a situation, you have a k, that scaling factor, and that scaling factor goes to infinity. The only way to have a finite output, you can see from that equation with k in it, is that if k goes to infinity, the only way for this to become be still finite is for ui plus to minus ui minus, that term in the parentheses, to be 0, to go to 0. And that means that the two inputs would be asymptotically equal. Now, these two inputs, as we said before, can be voltages or currents or either one of those. So it forces these two inputs to be equal. And this is a very important and useful feature, this asymptotic equality, because it allows you to make very simple calculations to determine the behavior of a net feedback network. And I can use it, and then you can use that result in the design phase. So let's do a couple examples to see what we mean. So the first one is an actual voltage op-amp. So let's start with an actual voltage op-amp. So you're probably familiar with this. It's an amplifier voltage input, voltage output. The output voltage is the difference of the two input voltages within the range of voltages, as long as you don't exceed that range. And first we have to verify that it's a negative feedback. You can easily see that the output is applied to the negative input. So if one moves up, then what comes back is going to move down. So now let's apply the asymptotic equality principle. So let's say k goes to infinity. If k goes to infinity, what it means that for h infinity, these two terminals, the plus and minus input to terminals, are going to have the same voltage, which basically means that Vi minus will have to be equal to Vin. So if and that makes the calculation very simple, because if Vi minus is equal to Vin, there's a simple relationship between Vin and Vi, which is shown here. So Vin can be written as a voltage division of a resistive voltage division of V out, basically V out times R1 over R1 plus R2. And then you can basically solve for V out over V in under K going to infinity, which is by definition H infinity, which is the asymptotic transfer function. And you can easily show that it's 1 plus R2 over R1, which is the familiar result for a non-inverting amplifier state, the op-amp stage. Now, by the way, in terms of type of feedback, this is basically series shunt, because the voltages are subtracting from each other at the input, and the output also, you're sampling the voltage in parallel. So you're sensing voltage and returning essentially a voltage. Now, The other thing that basically you have here is that, so now this is a second example. So let's do a transistor level example. So now look at this circuit. And again, we have a similar situation at the input where you have the difference of the two voltages, some of the output voltages subtracted from the input voltage through the gate source of the transistor M1. And basically, then it's brought back. So first we need to check the sign of the feedback. So let's say the gate of M2 transistor moves up. That's a common source, so that it's an inverting stage. So V out is going to move down. As a result, it's going to lower Vi minus, and that goes through M1, and M1 for Vi minus acts as a common gate. So basically, it's going to be non-inverting. It's going to be pushed down. So you can see that it's negative feedback. Now, under asymptotic equality, we would think that basically that V in and Vi minus should be equal. But let's do a little bit of more detailed analysis to make sure, since it's one of the first examples. So let's look at the small signal model. So here we have the small signal model for that circuit. We've used the pi model for transistor for M2. And to make things easier to see, we've used the T model for the transistor M1. And now what you see is that if you take the scaling of IS, so you put an KIS in front for that dependent current source. And again, I emphasize it's important to use and add a scaling factor, not change the transistor parameters. So if you take K to infinity, what you see is that to get a finite V out, of course, you have to have a finite V pi, and to have a V pi 2, I mean, and to have a finite V pi 2, you basically need to a K, and under K going to infinity, the only way is that IS1 has to go to 0. Because that product needs to remain finite, which is the current of that first current source. And that means that basically IS1, the current through RM1 is going to be 0, which means that V in and Vi minus are going to be equal. And again, you have a very similar expression as before. So basically, you can write V in and V out are related to a voltage divider ratio of R2 and R1, which you can show, which we have shown here on the top, right? And then from that, you can easily calculate H infinity. The asymptotic transfer function is 1 plus R2 over R1. And this is basically a very useful parameter. For example, if you were to design this amplifier, you would quickly want to kind of like come up with something that a quick and dirty first pass design. You say, okay, I need a gain of 10 from this amplifier. Well, you need to make the ratio of R2 to R1 like 9. So you can make R2, for example, 900 ohms and R1 100 ohms, for example, or any kind of like scale up version or scale down version of that, depending on your current levels. So if you make R2 900 and R1 100, you're gonna get a gain close to 10, and we'll see what the correction factors are later. So this is a third example. So we have another example here, which basically is what we have here is that we use a bipolar transistor, just to show another example, and it's a shunt input. So basically the currents at the input are subtracting. So now in this case, you can see that your UI plus and UR minus are two currents. And then the output is a voltage. So you're sensing voltage and returning current. Now, in this case, what you see is that, again, if you take the K, if you scale the GMV pi of the transistor, we're using the pi model, and introduce a K in front of it and take K to infinity, again, as we can see, this is a negative feedback. So to have a finite output, you need to have a V pi that's 0, and which basically means that IB, the base current, is going to be forced to be 0 by feedback. So which means that all of the current input current I in is going to go through R2. And those two currents are going to be asymptotically equal, which basically means that you can write I in as I of R2, which basically simply, since the left side of R2 is at 0 because of the feedback, again, V pi went to 0. So that current is simply going to be V out, negative V out over R2. And from that, you can easily calculate the asymptotic transfer function of this circuit to be negative R2. So if you want to use, for example, a transconductance amplifier with a transconductance of, I don't know, 2 kilo ohms, then you make R2 2 kilo ohms. And that would get you something that's very close to what you ideally would like to get. So that's the background of the asymptotic feedback, asymptotic transfer characteristic. And the interesting thing about this analysis is that it also give you additional insight about other features of, feedback. So we'll spend the next few slides talking about some of the interesting things that the feedback actually does and reviewing that. So the first thing we are going to do is that we want to see what is the impact of feedback on the dynamics in the forward path. So now imagine that your A has some dynamic, some frequency dependence, it's A of S. And of course, the transfer characteristic still would be the same as with A of S. But what you see is that when the AF is much greater than 1, basically the denominator is dominated by that, your transfer function basically reduces to your H infinity. So it's going to be 1 over F or H infinity. And when it's much smaller, then it becomes simply the open loop transfer function. So A of S itself. So this is a way to visualize it. So on the left-hand side of this plot, which is basically when your blue curve, which represents the open loop transfer function of the open loop amplifier without feedback, what it does is see that it lowers the gain when you have that excess gain and you have a lot of it. It lowers that gain to the level of H infinity, which is 1 over F. So basically you reduce the gain. And that's basically what feedback does. It reduces the gain when you have too much of it, but it makes it controllable by a parameter that's better controlled. Usually the feedback network is made in a simple fashion that in a lot of amplifiers to make sure that it's less dependent on the parameters and things of that sort. And you can see on the right-hand side of this plot, what happens is that you are getting essentially whatever you had already from the closed loop, from the open loop transfer function, A of J omega. So you basically, what your transfer function is the same as what it would have been without feedback. And a lot of more interesting stuff will happen in the transition region, which basically goes back to our analysis of stability and the gain, and which is interesting that we'll discuss in a later video, and it's also in the lectures video. What happens in that is a subject of a very useful, interesting conversation. But what you see is that basically this is what it does to the forward dynamics. So the forward dynamics, you see the behavior, the ups and downs of the blue curve on the left-hand side are suppressed and they are flattened and much more controlled because that is basically removed. Now, next question is that, and this is an example of that before we get to the next question. Here's an example, simple example. So imagine a first order system. So let's imagine your dynamics is just like first order as shown here. And then if you plug it into the equation and do the basic calculation as you're probably familiar with, what you see is that this applying of feedback is lowering the gain by a factor of 1 plus A0F, which is the low frequency gain. And at the same time, increasing the bandwidth by exactly the same factor in the first order system. So in the first order system, that you can see that this just transition is almost perfect, meaning that your gain is lowered to the level of A over 1 plus AF, which for large A0, it can be close to 1 over F. And at high frequencies, it's basically just going to follow the response of the system. And you can see by lowering the gain at the points that you had too much gain, you have increased your bandwidth from omega naught to omega naught times 1 plus A0F. So this is classic bandwidth enhancement in feedback, which is achieved by lowering the gain when you have too much gain. So you have a more flat gain across a longer range of bandwidth. Now, the interesting question is now what happens if you have dynamics in the feedback path itself? So now we are assuming that the dominant dynamics is in the feedback path, capital F of S. And if you again apply the same asymptotic principle, asymptotic transfer function calculation and take k to infinity, what you see is that basically reduces to 1 over F of S. So which is interesting. So H of S, the closed loop transfer function, is the inverse of what you put in feedback, which is actually kind of again repeating the same pattern. If you remember, originally H of infinity, we calculated H infinity to be 1 over F. So even for scalar feedback, the forward transfer function, closed loop ideal transfer function asymptotically is going to be 1 over the feedback, as there's an inversion. So here also you see that the transfer function also inverts. So basically the poles of the feedback network become zeros, and the zeros of the feedback network becomes pole of the closed loop system. Now, here's an example. So if you look at this feedback network from right to left, it basically consists of the resistors R2 and C and capacitor C and the resistor R1. And if you look at that network from right to left, it is essentially a high-pass network. But when you put it in a feedback network and apply the asymptotic equality principle, you will see that the input current IN plus and IN minus have to be equal. And in that case, what you see is that based on the calculation that's shown down here, which is a very straightforward calculation, H infinity is going to be negative R2 over R1 times 1 plus R2CS, which basically shows a low pass response. So the zero that you had in the transfer function of the high pass network has become a pole, in the transfer function of the closed loop system. So this is another example of feedback inverting, whatever you put in the feedback path getting inverted. And this is actually a more general principle that happens more frequently, as we'll see. So now let's talk about nonlinearity. What happens to nonlinearity? Now, imagine that you have, first assume that you have some nonlinearity in the forward path. We are showing it as an extra function g here, which captures the nonlinearity. So you can solve it for any general nonlinearity. So you can say y equals g of ka x minus ui minus. And ui minus is basically f times y. So that equation you cannot solve for y in terms of x. Well, it's difficult because you need to know that. But you can actually solve it for x in terms of y. And the solution is shown right underneath. So x is going to be f times y plus g inverse of y over ka. Now, let's see what happens asymptotically. If you take k to infinity, the second term is going to disappear because the denominator is going to become very large. And what you see that the effect of nonlinearity disappears, and basically x becomes fy. In other words, y over x asymptotically is going to be simply 1 over f. So you are still going to get the 1 over f. And this is another example of how feedback reduces the nonlinearity in the path in general, for any general nonlinearity, because of that k that happens in the denominator in that expression above. Now then, here's an example of that. So think about this circuit that we've looked at. So we have this feedback network, and let's do a large signal analysis of this thing. So large signal analysis, Vin minus VBE of the transistor is going to be the current through R1, and let's assume that beta is very large, and then that's going to be VBE minus V out over R2. That current, most of that input current is going to go through that R2 resistor. And if you write basically VBE as a small, solve for VBE, and they're just shown below, and then approximate it as the capital VBE, that's not changing a lot, then you can write an expression for V out in terms of V in and VBE. And what you see is that this is actually a linear expression. You don't see the exponential, it's a linearized expression. And this is a simulation showing exactly that. So in the absence of that feedback network, you see the first curve, which has a higher gain, but you can see it's quite more nonlinear. You see that exponential behavior. And then what you see in this case with the resistor of 5K and 1K, you see that once you apply the 5K R2 resistor, it has become linearized. You can see a negative gain of approximately 5 in that slope of that straight line, and you can see an offset of about like 4.1, 4.2 volts, which is coming from the second term in the expression. So you can see that this linearization actually happens in practice. So now the interesting question is that what happens if you have nonlinearity in the feedback path itself? So again, you can write the expressions that's shown here. So you can express y in terms of the difference of the two inputs. And now the second input ui minus is f of y. Again, you can basically solve for x in terms of y. And when you do that, you will see x equals f of y plus y over ka. But now this time, if you look at it asymptotically, k going to infinity removes the second term. So basically you get x equals f of y, therefore y equals n f inverse of x. So you see that again, the function, the transfer function of the forward path asymptotically is going to be inverse function of what is in the feedback path. So for example, if you put an exponential in the feedback path, you're going to get a logarithm. If you put a square law device in there, you're going to get a square root dependence, and so on and so forth. So you get an inverse function. So again, it's another example of the feedback inverting the behavior of the putting something in the feedback path will invert its behavior in the transfer function of the closed loop system. So you see the inverse behavior. So this is now not only applied to transfer function and scalar, but also it's applicable to nonlinear functions. So if you put a nonlinear function in the feedback path, you can actually invert it. It's quite a useful tool if you want to generate some nonlinear behavior. So in general, all of these things really boil down to the fact that another way to see this is kind of like an incremental analysis or sensitivity analysis, which basically means that you can determine that the sensitivity of your forward path gain, closed loop gain, to relative to the variations in the forward gain, the open loop gain, as well as the feedback. And you see in the first expression, dH over H, which is the fractional changes in the closed loop gain, is a scaled down version of the variation in the open loop gain. So the open loop gain variations are reduced by a factor of 1 plus AF, which is a significant reduction. Now, at the same time, if you do the same analysis for feedback, you see that the same thing doesn't happen. You see that the variation in the feedback, dF over F, are almost exactly reflected in the transfer function. And that's why it's important to make sure that if you are trying to make a stable transfer function, to make sure that your feedback network is stable, because your stability is really limited by that, because that factor for large AF is close to 1 or very close to 1 that you see in the bottom. So this is the basic calculation of the asymptotic transfer function. But we said earlier that there are correction factors to get the exact result. If you want to see what is the error in the calculation when k is not infinity. So because of course k is not going to be infinity, and then you want to find how those calculations work out. So we'll basically rely on a method which is basically based on the return ratio. Now, return ratio is a very interesting and valuable quantity that was defined by Bodie initially, and it is a way of dealing with how much of the signal that a source generates comes back to it. So imagine that you have a dependent source like the one shown on the left-hand side, somewhere inside your circuit. So there are a lot of transistors and things of that sort, and there's a dependent source. It can be a current source or a voltage source. So in this case, it's shown as a current source, and it has a gain of GU of A. So there's some voltage that it amplifies by G. Now, what we are trying to do, essentially, the essence of what we are doing is that we are replacing this current source with an independent current source. We call it IX, and we see what that dependent current source would have gotten back. Now, one practical way to do that is shown on the right. So the more practically, what we do, we place another current source in parallel with your dependent current source, and the sum of those two current sources would be what we call I of IX. And what comes out of your dependent current source is the return value, which is IY. And the return ratio shown with T is defined, and the ratio of, in this case, IY over IX, or in general, if there could be voltages or currents in general, so they would be UY over UX, which could be IY over IX or VY over VX. So now, one of the important points to keep in mind is that if you do it this way, you have to remember IZ should never enter your equation. So you start with an IX and calculate an IY. IZ is a way to just make sure that the KCL is held in place. So you can independently control IX from what comes back from IY. So it's a practical way of showing it that makes sense, and it's easier than removing a current source and putting an independent current source somewhere else to see what comes back. So this is a more practical way of doing the same thing. So now, if you have that, and what can be proved that is the overall transfer function is exactly given by this expression, which is called the asymptotic transfer function formula, or asymptotic gain formula. So which basically says H infinity, which is the asymptotic transfer function we calculated before, times the return ratio over 1 plus the return ratio, plus H0 times 1 over 1 plus T. So we are familiar already. We've defined T and H infinity, and we will see a few examples shortly. H0 is what we call the direct forward transfer. Basically, it is the transfer when you set K to 0. So basically, you disable that source. A lot of times that source, basically, you choose that to be part of the main part of your feedback. So you say you're disabling the feedback, the main part of not feedback, sorry, the main part of your forward path, and you're disabling the forward path, and you see what's the parasitic amount of signal that goes through the rest of the network, including the feedback path. So the feedback path can send signal back from the input to the output in general, because it may not be unilateral, and that effect is basically captured by H0. So the key important thing about this formula is that this is an exact formula. This is not an approximation. This is an exact formula. So you can actually find the exact transfer function. However, all three of these parameters should be calculated with respect to the same source, meaning H infinity is when a K in front of that source is infinity. T is calculated when K is essentially set to 1 and the return ratio is calculated. And H0 is calculated when K is 0. So if you calculate these for different sources or different parameters, then you will not get a correct result. But as long as you do it for the same source, you will get the correct result. So this formula can be written also in the multiplicative form. So you see in the previous slide, we had it in the additive form, there are two terms, but you can actually have it in the multiplicative form, where basically the asymptotic transfer function is multiplied by two correction factors. One is dt, which is the correction for the finite return ratio, t over 1 plus t. And the second one, which is a correction for the parasitic signals feeding from the input to the output in paths other than the main forward path. And that's captured by D0, which is given by 1 plus H naught over T times H infinity. And this is, you can basically derive the second one from the first one by just factoring these terms. It's not that complicated. So now let's see a few examples to see how this works. So consider the following shunt series feedback network, which basically senses the output current and returns an current to the input. Now, we want to determine, we know that we need to determine 3 parameters to determine the exact transfer function, H infinity, which is the asymptotic transfer function, the return ratio T, and the direct forward transmission H naught. So, and we need to also first of all, whenever we try to apply this asymptotic equality principle, we have to first check that the feedback is indeed negative feedback at low frequencies. So in this example, so consider that the gate of M1 moves up, goes up, and the voltage goes up. So what happens is that the voltage of the drain, because it's an inverting stage, is going to go down, which is the gate of M2. So that voltage is going down, which is going to push the source down, because from that perspective, it looks like a source follower. And that would push that voltage going down on the right-hand side of R1 will pull down the voltage on the left-hand side of R1, which is the gate of M1. So you can see that's negative feedback. So now let's start calculating the parameters associated with this. So we'll always start with H infinity because that's the most important parameter. That's your design parameter, right? So if you want to design something to have it, you can see this is like a transimpedance stage. The gain of this thing, the input is a current and the output is a voltage. So the gain of this thing has units of ohms. So we want to find out what it is. So let's pick, for example, the transistor M1 and scale its GM by a factor of K. So it becomes KGM, right? In that, if you can in your mind, you can think about the pi model in there. Now, for you to have a finite output voltage, the gate of M1 should be finite, which means that basically the drain of the gate of M2 should be finite, which basically means that the drain of M1 should be finite voltage. And the only way to get a finite voltage with an infinite K in the product of KGM1 V pi VGS, in this case, VGS, that in that product is for VGS to go to 0. So when VGS goes to 0, of course, the input current has to go to 0 because there's no voltage across that input, whatever impedance there is at the input. So all of the current I in, the input current, is going to go through R1. And when it goes through R1, you can easily see that that current will produce a voltage V2 of negative at the output, at the source of M2, which is basically negative R1 I. And from that, you can easily calculate what V out will be, because it's the sum of because that voltage V2 determines you can use that to calculate the current through R2 by dividing it by R2. So you get negative R1 over R2 times I in. And that, in addition to the current that going through R1, which is simply I in, is the total current that goes through the source that will show up at the drain. And that would be basically the current that's being driven into R4, which gets multiplied by R4 to give you the total output voltage. And from that, you can calculate your H infinity to be R4 times 1 plus R1 over R2. So this is a useful result, because if I'm trying to make a transconductance stage, let's say transimpedance stage of, let's say 5 kilo ohms, right? So you can make R2 let's say 500 ohms. And then you can make R1 and R2, like let's say R1 900 ohms and R2 100 ohms, and R4 can be 500 ohms. So R1 over R2 ratio becomes 9 plus 1 is 10 times 500 ohms of R4 gives you 5 kilo ohms. So you can see how quickly you can design, if you understand this principle, have a first pass of design without writing a lot of equations. So now let's see what are the correction factors. So first is the return ratio correction factor. So we'll use the same source, which was the current source, dependent current source in the pi model for M1. And we apply the current IZ in parallel to generate IX and IY. So if that's IX, the voltage on the drain is very simple. It's going to be IX basically times R3. And that current is going to produce, that voltage is going to come now and generate a voltage across R2, which is going to be IX R3 times R2 over RM2 plus R2. And that basically from that perspective, you can, once now that you have the gate voltage of M1, you can calculate IX by multiplying by GM1. And that produces the return ratio that's given up here, which is basically shows you that it's GM1 R3 over R2 over plus RM2 plus R2. And now if you want to convert this to a multiplicative factor, you can always use that expression that we have on the bottom. And then what you see here basically is just that you can see, as you can see here, basically you have an expression for the T over 1 plus T. So one of the things to keep in mind is that now the other parameter that we need to calculate is basically the direct forward transfer, right? H naught. And in this case, basically that's calculated by setting K to 0. Now you can see if you set K to 0, there's no signal transition at low frequencies through the M1. But there would be some signal transitioning through, getting to the output through R1, M2, and M2, right? And you can easily calculate that. So if you have an I in with K equals 0, all of that I in is going to go through R1. There's going to be a current division between these two values, between the two branches, R2 and the RM, which is the resistance seen in looking to the source of M2. And that current basically is going to be I in times R2 over R2 plus RM. And that current appears directly at the output, gets multiplied by R4 to generate the output voltage. So you can see that the direct transfer function is R4 over times R2 over R1, R2 plus RM2. So these are the two correction factors that you would need to make the correction. So here's another example. The Cherry Hooper amplifier can be a stage can be a useful stage as a load or an amplifier. So one of the things that it can be useful for is that to present you can use it to do peaking. You can basically control the quality factor of the load that you present without using an inductor, for example. You can actually create some peaking in the transfer function and enhance the bandwidth. And one of the things that you can do is basically by using this stage, which is an interesting stage because in this case you can see there's nonlinear active feedback in the feedback path, and this is something to be kept in mind. So the price you pay is that you have nonlinearity in the feedback, and you have the inverse of that nonlinearity appearing in the forward path. So what still we need to determine the H infinity, the T, and H naught for this stage. So let's look at this one step at a time. So let's start again, as always, we first always start with the H infinity. And basically H infinity here, what you have is that to determine that, we will use the current source, the dependent current source in the pi model of M1 and scale it by factor K. So now if we scale it to factor by K and taking K to infinity, the only way that you can have and this is negative feedback, the only way you can have finite output is by the product of K GM1 and VGS1 being 0, which basically means that as K goes to infinity, VGS has to be 0. Basically, the gate and source have to be asymptotically equal. And at the same time, that also forces the fact that the current has to be 0 because there's across that incremental AC impedance, you have no voltage, therefore there would be no current. So I in all of the input current, the small signal input current, has to go through R3 as shown in this figure. And this basically means that the gate voltage of that transistor needs to be controlled. But so all of that current going there basically means that the gate voltage has to be given by R3 plus RM2. So that expression should say R3, not R4. R3 plus RM2, and then that is the voltage that you see at halfway between R1 and R2, and then that voltage is related to V out through a division, which is going to introduce that second term 1 plus R2 over R1. So the H infinity asymptotic transfer function gain in this case is going to be negative R4 plus RM2 times 1 plus R2 over R1. And you can use the parameters of this thing to adjust your load resistance, if you will, effective load resistance of the Cherry Hooper, given by this expression. Now, in this example, the way it's drawn at low frequencies, basically H0 is going to be 0, because once you set K to 0, then what happens is that there's no path for the signal to get from the input to the output, because it's not going to go back to the gate of the transistor M2. So that's, in this case, H0, the direct transfer is 0. How about the return ratio? The return ratio in this case is given by, as you can see, you can apply an IX. That current is going to go through R1 to produce the gate voltage of M2. And that voltage is going to be reflected directly at the gate of M1. And that's going to go through GM1. So you get R1 and GM1 as the return ratio. So it's GM1 R1 is the return ratio that you can calculate for this. Now, how about high frequencies? You may say, okay, what's the high frequency behavior of this thing? And that's an interesting question, because that's the one that actually affects the dynamics. So let's look at that a little bit more carefully, and it's a useful example. So what you have in this case, again, is that, so now assume that you have two capacitors. We're just taking two capacitors into account, C1 and C2, the input capacitance, the gate capacitance of the transistor M1, and then we have a C2 capacitance at the output. So if you're taking these two, again, if you can do a similar calculation for H infinity for the asymptotic transfer function. And you will see that it's going to be the same, because if C1 has no effect, because the voltage across it asymptotically when k goes to infinity, interestingly, is 0. So there is not going to be any current flowing through C1. So C1 does not play a role in H infinity. Neither does C2, which is actually a more interesting reason, because whatever the effect is, the voltage across that is defined as V out. So we've defined it as V out. And whatever the V out is going to determine V in, the relationship with V in. So H infinity is going to be the same expression again with R3, that R4 should say R3, negative R3 plus RM2 times 1 plus R2 over R1. And again, interestingly enough, if you set k to 0, there is no path for signal to get from direct transferred from the input to the output. So if you disable that transistor, if you will, if you make its current source go to 0, there is no path. So H0 is also 0. So neither H infinity nor H0 have actually changed with the addition of these two capacitors. Well, something has to change, because this will affect the dynamics, and that's exactly what's affected, which is the return ratio itself. So what you have in this case is that, so let's calculate the return ratio here. For calculation of return ratio, again, we introduced that IZ, and IZ is going, basically that produces IX. So IX is going through R1 again, and then if there's now this time you have a divider between the RM of M2 and R3 and C1. So there is that division ratio happening there, and then that's going to be fed back. Now, what we can do here is that we can actually use the method of time and transfer constant. And notice that the time constant associated with C1 and C2 are uncoupled. And the way we know that is that if you short or open C1, the resistance seen by C2 is not changing, and vice versa. So you can actually calculate two independent time constants and plug them into the expression and use the low frequency the low frequency calculations that you did for the return ratio to calculate your high frequency one. And what you see here in this example is that you can calculate two time constants. The resistance seen by C1 is R3 plus RM2. So therefore that's time constant tau 1. And the resistance seen by C2 is R1 plus R2. So you can see that you have two time constants, and since they're uncoupled, you can factor the denominator and write it as in the form that's shown here as the product of 1 plus tau 1s times 1 plus tau 2s. And now if you put it into the multiplicative form, which is shown on the bottom, what you see here is that you get your low frequency transfer function, low frequency return ratio, which is shown on the left hand side, the correction term, which is low frequency. And now the only term that has dynamics is the term on the right hand side, right? And what you see is it produces a second order term. Now this second order term involves tau 1, tau 2, and T0, which is the low frequency value of the return ratio. And you can see that you can actually control this dynamics by controlling the low frequency value of this return ratio. And this is a more specific details of that. So what you see is that the transfer function is given by this expression on the top, and the only part that has dynamics is the last term, that's fraction. Now, for example, we know that if the quality factor of a second order term, Q of the second order term exceeds 0.5, then you get complex poles. So what happens is that as you increase T0, the low frequency return ratio, by adjusting it, you start off with the two blue poles that are shown on the real axis, and these two poles start moving towards each other as you increase it, and then they hit each other at this exactly the value which sets Q2 equals to 0.5, which is shown in purple. And after that, you produce a pair of complex conjugate poles that you can control, whose damping rate factor or quality factor you can control by adjusting the value of T0. And this is T of 0. So by the low frequency return ratio. So you know exactly what knob you need to turn to control, and you can actually control it the right amount to get exactly the right amount of peaking that you may need in your transfer function. That's how you design using a Cherry-Hooper amplifier, a Cherry-Hooper stage. So this is another example. So now the next topic we're going to talk about is basically Blackman's impedance formula. So this is also a very useful thing. This is a helpful tool for determining the input and output port, or generally port impedances in a feedback network. And more importantly, it's a very useful design tool, because a lot of times you want to use it to design a feedback network. A lot of times you use a feedback circuit to control the impedance. You basically want to create a fixed impedance or low impedance or high impedance. And this is basically the way to deal with that. This is a very effective way of dealing with that. So here what you have, the formula is given on the top. Basically, it says that the port impedance of any port is given by Z naught, which is basically the impedance you see looking into the port when you set the reference source, like we did before when we had a K times a dependent source. When you set the K of the reference source to 0, and then you have two parameters, T short and T open, which are two return ratios calculated for the same source. So you calculate the return ratio for the source twice, once with the port of interest, the one whose impedance we are interested in, shorted, and another time with the same port open. And that basically gives you the expression. So you can basically from that tell what the impedance is going to do. If you want to lower it or how you know what you need to do to the T, so you want to make sure that T short is smaller than T open or larger. And more importantly, also kind of like you can use this to design and tell what kind of feedback you have, because if you're lowering the port impedance, it's going to be a short. If you're increasing the port impedance, it's going to be if you're lowering the port impedance, it's going to be a shunt, and if you're increasing the port impedance, input or output, it's going to be a series. So these two are the definitions are given down here. So you can see that the definitions are consistent with what's said. The port impedance by K is 0, and the T open and T short basically are determined by that. Now let's see an example. So let's use our Cherry-Hooper stage again as an example and see what happens to its input and output impedance in this case. Well, the input impedance in this case. So what we are doing is that we are interested in the input impedance. And so we use the source of interest as the current source in the hybrid pi model of transistor M1. And let's say we set the K to 0. If K is 0, the only impedance that's left to be seen is the resistance looking through R3 through the into the gate, into the source of M2. And that resistance is R3 plus RM2, as we know. Now, if you short the port, the input where the blue arrow is, if you short it to ground, you will see that no signal is going to return. So the return ratio for the source IX is going to be 0 because the voltage of the gate of M1 is grounded. So there's no signal returning. So the return ratio for short is going to be 0. But the return ratio for the open is going to be the same thing as we had before, which is what GM1 R1. We have calculated this return ratio before already. So it is basically that. And from this, you can easily see that now this arrangement that is lowering the input impedance, it is a shunt arrangement, which is lowering that. So you can see the two currents are subtracting, if you will, in the input. If that's another way. And you can calculate the effective input impedance simply by the expression by Blackman formula, which is shown in the last equation down here. So basically, what we have is this is an example. So now let's do another example for the output impedance of this stage that we had before. Now, here in the output, you have series feedback. So let's see what happens here. Now, we are looking at the output impedance, what we call R out prime. R out prime is the resistance looking into the drain of M2, which will appear in parallel with R4. So we are ignoring the R4 part of this thing because we know whatever R out prime is, the total output impedance is going to be R4 parallel to that. So the really important part is R out prime. So R out prime 0, which is basically when the source that's chosen to be that of the transistor M1 is 0. So what do we see when we look into that? Well, what we see is basically the RO of the transistor times 1 plus GM2R2. It's the classic calculation for MOSFET with source degeneration. So that's the output impedance. Now, one calculation is the T short. What happens when you short circuit the output, right? When you short circuit the output, and remember, we have removed R4 now, right? R4 is not there. If we short circuit the output, then the return ratio is what it used to be. So that the calculation of the return ratio is going to remain the same. So it's going to be GM1, GM2, R2, R3 over 1 plus GM2, R2. Now, if you leave it open, though, the interesting thing is that whatever current that is in that current source will have to circulate through RO2 of the transistor M2. So none of that current will return. So for open, the return ratio is going to be 0 because no current can go down into R1 or R2 because all of that current, because the drain is open, has to come back through the source for KCL to be satisfied. And therefore, you can see that this being a series configuration at the output, it increases the output impedance, and the output impedance can be calculated as shown here. So let's summarize the kind of asymptotic feedback analysis. So what is it? It is useful for calculation of the gain and it provides insight. It's a useful design tool because you get, especially with H infinity, you can actually have a very quick first pass design that would come close to what you need, and also the loop, the return ratio will allow you to see how close you're going to be in addition to H0. Blackman formula is also useful for determining the input impedances as well as helping it for design. Now, and the interesting thing is that if you have a fully unilateral loop, the return ratio is the same for all of the sources that choose within that loop. However, the problem is that if you have bilateral loops in general, and in general, the choice of the source will affect the value that you get for return ratio. So the return ratio itself is not an invariant of the loop. And this is an important parameter because it is important, especially for stability analysis. When we look at the loop, the parameters of the loop, we want to pick something that's an invariant of the loop, preferably for a single loop. And the other challenge with return ratio sometimes is that it may be difficult to access internal source in an actual physical circuit, or the parasitic of the transistor if it's in the complex transistor model inside a simulator. So these basically lead us to another tool that we developed, which is the loop gain. Now, the concept of loop gain, idealized concept of loop gain is shown here. So basically, if you have a loop, and if you can see that simple kind of like system kind of loop that people show in the system theory analysis of feedback, not necessarily circuit theory analysis of the feedback, you can see that you can break the loop at any point and apply a signal UX and see what comes back. And the ratio of those two is basically what comes back to what goes in is negative AF, no matter where you break this loop. Now, the negative of this quantity is traditionally defined as the loop gain. So remember, when we talk about loop gain, we are talking about the negative of this quantity, the same way that there was a minus sign in the return ratio calculation. And that is basically shown with this other T. So to differentiate the return ratio from the loop gain, for loop gain, we use this T, this different font for T that's shown here. And that you can see that that's an invariant of the loop, right? And it's independent of the breakpoint. Now, the question is that in circuit, how do you break a circuit? Because if you break it, whatever was connected to it, the resistances, the loading impedances need to be taken into account. So you could also go and say, okay, well, this was the load that I had and put it there and calculate it, and it makes it a little bit more complicated sometimes. Or you could reduce it to two simpler calculations. You can actually do two calculations of the loop gain. One is what we call the voltage loop gain. So you apply a voltage source in the primary direction of the loop, which is the original direction. In this case, is clockwise in this figure. So you have a Vx applied, as you can see on the left, and see what voltage comes back as Vy when that other port is open. So you break it, you apply voltage source to the left side, and then you on the right, basically on the return side, you leave it open and you measure the voltage. So that ratio we call the voltage loop gain, and shown with T of V. And similarly, you can define a current loop gain, where basically you apply a current source to the same place that you applied the voltage source, but now on the other side, you now short circuit it. So the voltage is zero, and you measure the current. And this is basically called the current loop gain. Now, if you calculate these things in a unilateral loop, this relationship holds, which is very useful and very interesting, meaning that the overall loop gain of the system, the reciprocal of the overall loop gain, is the sum of the reciprocals of the voltage and the current loop gain. So kind of like they behave like parallel resistors, if you will. Now, interestingly, so this is for a unilateral gain, is also a unilateral loop. It's independent of the breakpoint. Now, this automatically takes care of the impedance level. So you don't need to really worry about what impedance levels you're working at or something like that. This automatically takes it into account. And a lot of times you can actually simplify it if you're doing analysis by choosing a location at which one of these loop gains become negligible. And remember, for loop gains to become negligible in this calculation, they have to be very large. So the one that goes to infinity is the one that is ignored because you're adding the reciprocal 1 over those things. So 1 over the infinities becomes 0, so they don't play a role in this thing. It's like parallel resistors. The big one doesn't matter. So let's see an example of how this works in practice. And this is, as you said, this is a useful thing, particularly for stability analysis that we'll talk about in a later video. So here, basically what you have, so we are taking the same circuit that we had as one of our examples early on, and we are going to break it into 3 different locations and show how, although the voltage and current loop gains are individually different in each one of these breakpoints, the overall loop gain that you calculate using this formula is going to be the same. So the first example is where we break it at the gate of M2. In this case, if you apply a voltage and measure the voltage, you basically see this relationship that you see. You can easily see that if you apply a Vx at X and measure the voltage Vy that comes back, it's a very simple circuit calculation. It's going to be GM1, GM2, R3 times R1 parallel R1 or M1. Now, how about the current loop gain? In this case, if you apply a current source into the gate of a transistor, basically the gate, remember, at low frequencies, the gate is infinite impedance. So right there, you produce an infinite voltage, and that's coming back around will produce an infinite current through M1, which basically through Y1 is going to produce an IY of infinity. So you see that Ti for this breakpoint 1, which we call it breakpoint 1, and we show all of this, the results for this breaking point with like the Roman numeral 1, is infinity. So basically, when you put it in that equation, the loop gain is going to be simply that of the voltage loop gain, which we calculated before to be GM1, GM2, R3 times R1 parallel RM1. Now, let's do another example of breaking the same loop, the same circuit, the loop in the same circuit at a different location. So now this time we break it at the gate, at the source of M1 connection to R1 and R2. So as you can see, again, we broke it there. We are applying the signal in a clockwise direction in the primary direction of the loop. So we are applying a voltage source at Vx and we're getting a Vy and applying a current source at Ix and measuring the current that comes back to a short circuit at Iy. And when you do those calculations, you can easily see that neither one of them is 0. So they're both non-zero. And if you plug them into the equation, though, in that equation, you will see that the some of the reciprocals of them are given as you can see up there. And what then you can see is that when you add them up, you will get exactly the same loop gain for the second breakpoint, which is shown with the Roman numeral 2 for overall loop gain. Although the individual voltage and current loop gains are different for this breakpoint, the overall loop gain is the same. Now, as a third example, let's break this loop at the third place, and this is basically at the drain of M1. Now, if you break it there and apply a current voltage source at Vx, now the interesting thing is that whatever that voltage is comes and goes around and will drive the source of M1. However, since the drain of M1 is left open and we are ignoring ROs here, that could produce an infinite voltage because it's as if you have a small signal resistance of infinity at the drain. So the voltage loop gain now is going to be infinity, but the current loop gain, you can easily calculate it to be this expression given here, which is again from the previous 2 examples. But if you again apply it to that equation that we had, you will get exactly the same overall loop gain. So what you see at the end is that the loop gain that we calculated were these 3 different breakpoints were different individually, the current and voltages, but the overall loop gain that you calculate for all 3 of them are identical. So this example shows that this actually works. Now, the question is that what if you have bilateral? What if you have a loop where the signal can go in the opposite of the primary direction? In these examples, it would be going counterclockwise. So basically going backwards through the amplifiers and coming backwards through the feedback. Now, if that is the case, you can still calculate the overall loop gain. There's a correction factor. And to calculate that correction factor, you need to define the reverse loop gains, which are shown here as TVR and TIR. So the reverse voltage loop gain and the reverse current loop gain. And the way they are calculated is that now this voltage source is applied to the opposite side and the voltage is measured on the other side while it's open, or a current source is applied to the opposite side in the opposite direction of the loop, not the primary, the reverse direction. And the current is measured through a short circuit on the other side. So these are the reverse current and reverse voltage and reverse current loop gain. And if you calculate these 2, one of the interesting things that you can show is that there is a general relationship between the forward and reverse loop gain. So basically the product of the forward and reverse voltage loop gain is the same as the product of the voltage, the current forward and reverse loop gains. And this combination is very useful. This identity is very useful because it allows you to calculate the full loop gain in a bilateral loop in by using the same equation that we had. The first two terms are the same, but there's a correction term, which is either the reverse current loop gain divided by the forward voltage gain, or the reverse voltage gain divided by the forward current gain. And this allows you to calculate it for a general in a loop in a general, which is a very useful quantity now because you can use it for stability analysis. Now, there's a lot more details to this and many examples. If you want to see more examples of these things, you can consult the book that you can download for free, the PDF of from our website, or you can also watch more detailed lectures that go in depth into these discussions with many more examples and proofs of the equations and all those things that can be found here. I hope you found this video useful and look forward to seeing you later.